So your homework number 5 is due on Thursday at noon, and then that's when I'll also post the solution for homework 5. We have an exam on Friday, and I wanted to check to see your preference about something. I've announced before that there's going to be at least one computer problem on that exam. And so there's 2 ways that we could do it. We could either have it be like the normal approach of you've got 50 minutes during class to solve both the paper calculation problems, concept questions on paper, and a computer problem. So that's the first alternative. Or the second is that I could give you the computer-based problems on Thursday at noon, and then that would give you 24 hours to solve the computer problems, and then it's just here in class that we would do the calculation problems that don't use the computer. So let's do, nothing's a democracy obviously, but I am interested to know the group sentiment. Would you rather have option 1, which is everything in the class, no out-of-class component to the exam? Okay, 0 votes for that. Now, of course, there is no third option. There isn't a let's not have an exam option. So, okay, what about the alternative of doing the computer problems kind of outside of class on your own time? Okay. I think maybe the preference is for that second option. So then that's what we'll do. At noon on Thursday, not only will the homework 5 solution be posted, but I'll also email, I'll have it released on Blackboard. So I'll set it up so that you'll go to Blackboard and then the computer-based problem or problems will be there. And so maybe that puts you less on the spot if your computer reboots, or if you prefer to use your desktop instead of your laptop. Maybe that just gives you a little bit more flexibility. So does everybody feel good about that?
So we need to make sure we can use H/8 StormCAT though.
Yep.
Okay.
Yep. And Excel.
Well,
Yeah.
okay.
Okay. So then that's what we'll do, and then in exchange for that extra time, I hope that you'll honor my request to work individually. That it's not a group effort. It's not something you check your answers with other people. It's just you and the computer, and 24 hours ought to be enough to get it done. All right.
I have a question about the exam.
All right.
What chapters will this exam cover?
Well, all of that's outlined on the schedule, so let's take a look at that. So here are the book chapters that you ought to review before the exam. So everything up to and including the infiltration material that we're covering today and on Wednesday.
Okay. Thank you.
Was there another question?
Not whenever, but do you have that flash drive that has the StormCAT download on it with you today?
No, I don't. No, but if you want to stop by my office, then we can get it on your computer.
Okay.
Other questions? All right. Well, let's talk about infiltration then. Just broad strokes, remember that infiltration is that fraction of the precipitation that isn't running off. Like if we were going to do a mass balance, there's water falling out of the sky. A little bit of it may be intercepted by buildings or trees. So there's sometimes a little bit less that hits the ground than comes out of the sky. But then of that fraction that hits the ground, some of it will evaporate. Even during a storm, there may be a little bit of evaporation. And then the rest of it will either wet the surface and be retained, or will run off, or will infiltrate. And so that's kind of like the mass balance. If we draw a control volume enclosing some portion of both the atmosphere, the surface, and the subsurface. The water is coming in and going out of that control volume, and what we're talking about is the infiltration component. Now, where we left off last time was just discussing this Green-Ampt equation. And what it does is it allows us to estimate both the amount of water that will infiltrate and also the rate of infiltration over time. And we talked about the declining potential rate of infiltration with this curve, how it's getting smaller and smaller in rate. And the reason for that, of course, is that, remember, the soil has a suction head when it's dry. It has an attraction to water that gradually is reduced the further down the water penetrates. And so as the water penetrates down through the column of soil, then it's just gravity drawing it from above. But initially, at the beginning of the storm, there's both the weight of the water and gravitational forces that are driving the fluid down through the soil, but then there's also the soil's attraction for the water itself. And so that's why at the beginning of the storm, the infiltration rate is high, but then it's declining as the wetting front moves down through the soil column. Now this is a table of just soil properties that we didn't get a chance to look at on Friday when we ran out of time, but this is just showing for different soil classes the porosity. Remember, the porosity is just the ratio of voids to the overall volume of the soil. So you'll see that it's some decimal, and the way to understand it is, for example, with a typical sand, if you had a cubic meter of sand, 43.7% of that would be empty space, and then the remainder would be the sand grains themselves. And so there's some space between the sand grains. And it's kind of remarkable that for each of these different soil types, the porosity remains about the same, approximately. Whether it's large diameter sand grains or very small diameter clay particles, you might be forgiven for thinking that if the particles are smaller, maybe they pack together more tightly and there are less voids. But they do pack together more tightly, but the ratio of voids to the overall volume is approximately the same. Here, 47% for clay, 43% for sand. But if you look at the range, there's a relatively wide range from 37 to 50% voids. All right, so porosity is just how much empty space is there.
Would that mean with like clay, like there's the occasional, just like a bigger like hole, like an air pocket?
No, it's not air pockets that is providing the porosity. It's just that the voids themselves are smaller. The particles are smaller and so are the voids. But the ratio of voids to overall volume is the same. Yeah, but I mean, you might think, well, it just must be big air pockets, but that's not what it is. Even for a compacted clay, the porosity would still be in this range. Now, effective porosity is similar to porosity, but there are going to be some voids that aren't connected to those around it. A non-connected void isn't able to transmit water. So if there was just a particle surrounding it so tightly on all sides that water couldn't get through, then that would explain the difference between porosity and effective porosity. Now, this third column, wetting front soil suction head, you can think of this as what is the intensity of attraction that dry soil has for moisture. And so the water is going to be drawn downward with quite a lot of suction pressure in the case of a clay. It's got a measured soil suction head of 31 centimeters. And that actually has physical significance. We'll look at a penetration test and a double ring infiltrometer, and there are ways to actually measure the tension that the clay is drawing down the water. And so at the other end of the spectrum, the sand has much less of a suction head, approximately an order of magnitude less. But then the last thing is we talked about Darcy's law and hydraulic conductivity. And so although clay has a very high attraction for water and the water enters the clay immediately. If you think back to the video that we watched, that YouTube video that was made in Belgium, the water got into the clay quickly, but then it goes through the clay slowly, whereas the opposite was true of the sand. In the case of the sand, the water didn't get in there very easily because it had to fully fill up all of the voids of the loam until the pressure inside the loam was low enough that the water could get into the sand. But then once the water did get into the sand, it moved through very quickly because it has a high hydraulic conductivity. So that video did a good job of kind of showing us both of these columns, the suction head effect and the hydraulic conductivity effect. And so we're going to use some of these typical values in an example to estimate the rate of infiltration over time. And Green-Ampt is a model. And we have to have some sort of a simplification to be able to make predictions of how much water is going to get underground when there's a rainstorm. And Green-Ampt is kind of maybe a medium complexity model. It has some simplifications that we're a little bit uneasy with. Like, remember, it assumes that the wetting front is just this binary initial water content and fully saturated, when really there's more of a curve and a gradual increase in the moisture content rather than just going from immediately initial water content to all the way saturated. But the Green-Ampt isn't the most simplified approach to modeling infiltration, and we'll look at a method that's even a little bit more crude and approximate than this. But let's just get a feel for how Green-Ampt works, and we'll do that by looking at a silty clay soil that has these characteristics. And so these are just some mid-range values that come from that table we were just looking at. An effective porosity that we know, the soil suction head for silty clay soil. So it's relatively high suction head because small diameter grains have a ratio. Particles have a negative charge, and the more surface area to volume, you're going to have a greater density of negative charge, and that's what largely drives the soil suction head, is the fact that you've got a lot of really small diameter particles in something like a silty clay soil. But the hydraulic conductivity is low because the water can't get through those small diameter voids very easily. The head loss is high through a small diameter pipe, right? If you have a small diameter pipe, then the water velocity is going to be slow for a certain driving force. And that's effectively what a soil column is. If you think about, you've got particles interspaced with voids. And so when water goes down through the soil, it's kind of like going through a very small diameter tube. And the tube is just those interconnected voids. And so in the case of something like a silty clay soil where the voids are very small, it's going to be penetrating slowly because of the high head loss as it passes through. All right, so we get a feel for the formulas that we're going to use here. What this is asking us to do is calculate the infiltration depth, so that's capital F, and the infiltration rate, which is lowercase f, after both 0.1 hour and 0.2 hours. We're going to assume the initial effective saturation of 45%, and continuous ponding just means that the rainfall intensity is at least as high as the infiltration rate. So that if it was raining less than the infiltration rate, then the water isn't actually going to absorb as much soil as its maximum potential rate of infiltration. If the soil can take like an inch per hour and we're only putting half an inch per hour into the soil, then it's not going to achieve the penetration speed that it would otherwise. Okay, now I've put in a note here that we're going to need to use solver and not goal seek, and the reason for that is that we're going to have the left-hand side and the right-hand side of this equation for infiltration depth. We're going to try and find the difference between the two, and we're going to set our goal, well, we're going to set solver to minimize the difference between the two, and it would quit early if we use goal seek. In goal seek, If the left and the right are pretty close, then it'll stop calculating, but we need more precision than that to get it to work. So I'll show you what I mean by that. Okay, so open up the template file that I put onto Blackboard. Has anybody else been able to download it? Is this what it looks like, the template file?
Yep.
Okay. So we'll start off by putting in the effective porosity. What the example said is it's 0.423 is the effective porosity. And remember, that's similar to the porosity, but it's just taking into account the voids that aren't connected to other voids. So like lava rock would have a very low effective porosity because it's a very porous substance, but a lot of those voids aren't connected to other voids. It's just they're completely isolated and surrounded on all sides by the rock itself. But this isn't lava rock, this is our silty clay soil. So we've got effective porosity of 0.423. The suction head, 29.22 centimeters. And then the hydraulic conductivity, 0.05 centimeters per hour. The initial effective saturation, 45%. So we'll put that in as a decimal, 0.45. And delta theta we calculate with this equation. Okay, so delta theta, that's the change in the water content when it goes from before the storm and after the storm. So this is how much additional water is going in there. So 1 minus the initial saturation. So that's with the 1 minus that, it's effectively how much extra space is there to add water. So that's the part that doesn't have water in it yet. And then we're multiplying it by the effective porosity, because obviously the soil grains aren't going to hold water. And so this is where it kind of goes with how I said, if you have an inch of water going into the soil, it's going to penetrate more than an inch because the soil grains themselves can't be filled by the water. And so there's only a certain amount of unoccupied space underground. And so the penetrating depth is greater than the depth at the surface of the water. All right, so 0.232 is our delta theta. All right, so we're going to use that here, first of all, with our calculations for infiltration depth using a capital F sub t. And so this is asking us to predict at 0.1 hours what is the infiltration depth. And so F sub t, we're just going to have a guess value because we don't know what it is yet. So you can see here it says start with a guess value. And the reason why we have to start with a guess is it's both on the right and the left-hand side. So let's just say, what if it was 1 centimeter? Okay, so what if in 0.1 hours it had infiltration depth of 1 centimeter? So then let's type in what's the right-hand side of that equation, referencing this as our F sub t. Okay, so it starts off with K times T. So K, and I'll anchor the reference there because later on that'll enable me to drag down to the next row for 0.2 hours. Okay, so K times this time, so after 0.1 hours, which is 6 minutes, plus, okay, psi, anchor that reference, times the delta theta, anchor that reference. All right, now times the logarithm ln, and inside the parentheses we'll have 1 plus, and for F sub t, I'd normally click on the location, but I've got the formula centered so that now it's kind of clogging the space, so I'll just have to type in B10. And so that's the location where we have the F sub t. And F sub t is divided by, let me put this in parentheses, the psi, anchor that reference, times the delta theta, and anchor that reference. All right. A typo. I won't let it figure out my typo. Oh, okay, I need one more parentheses to close out the logarithm, because I'd had that parentheses at the beginning of the logarithm. That ought to do it, I hope. Okay. So my left-hand side of the equation is 1. Right-hand side of the equation is 0.938. So the difference between the two is just this one minus that one. And my goal is I want the difference to be 0. That's how I know that I've got the correct f sub t. So I have to change my guess here, the left-hand side of the equation guess, until the difference is 0. So for instance, if I said 0.9, my difference is smaller. If I say 0.8, my difference is smaller. So just for kicks, let's see what we get if we use goal seek, because I've emphasized a couple of places you got to use solver, but I suppose it's always possible that in some newer version of Excel they have made goal seek insist on better convergence. So what if analysis, goal seek. Okay, so we want in this goal seek this difference to be 0 by changing our initial guess for the f of t. All right. So it'll keep changing this left-hand side guess of f of t until the difference is 0, or what it thinks is 0. So go ahead. Oh yeah, that's pretty good. But that's not exactly right. That's pretty close, but there still is some difference, right? We want the difference to be smaller than that. So it quit early. It's pretty close, but it's still off by a few thousandths of a centimeter. And so let me show you how Solver does a little bit better. So if you don't have Solver installed, you can get it installed by going here on the File tab under Options and then Add-ins. And then down here, Manage the Excel add-ins, go. Boy, this is just buried so deeply. And click the button for the Solver add-in. Okay. So then when you do that, over here to the right on the Data tab is now the Solver tool. It's a great tool, but for whatever reason, it makes Excel open a little bit more slowly. Like instead of 1 second, it takes like 4 or 5 seconds for Excel to open when you've got Solver enabled. So that's probably why they don't have it enabled by default. So click on Solver, and so what our objective here is that we want this difference to be value 0 by changing this initial guess. And then when we click Solve, okay, there it goes. So it was saying 267 before, and we had some non-zero difference. Now we've got 264, and that difference is better to a lot more zeros. So, okay, and the reason why it gave us that different answer is just if you get down here into the options for Solver, you can tell it what kind of precision you want it to look for before it quits. And so in the case of goal seek, there's just fewer zeros before it thinks the answer is close enough. So we wanted our difference to be really close. So I just increased the number of zeros in that constraint precision. All right. Okay, so what that tells us is that after 6 minutes with this kind of soil, assuming that there's at least 0.264 centimeters of water that has fallen from the sky in those 6 minutes, then that's how much will infiltrate. So this is the maximum rate of infiltration for this kind of soil during the first 6 minutes of a storm. That's the depth. And once we have the depth, then we could calculate the infiltration rate. By the way, before we move on to the infiltration rate, are there any questions, or did anybody have problems calculating the infiltration depth? Yeah, we've done way worse spreadsheets than this in hydraulics, right? This is an easy one by comparison. So, all right, well, let's do the infiltration rate calculation. Remember, this has units of centimeters, and so that's the depth of water. And if we think about the infiltration rate, then we will do K, anchor the reference there, times psi, anchored reference, times delta theta, anchored reference, divided by F sub t, so here's our infiltration depth, plus 1. So 1.34 centimeters per hour has been the infiltration rate during that period. Now I'm just wondering, like, why is it that we didn't just have this infiltration depth and divide it by 0.1 hours? Well, the reason why is that it's not a constant rate. We wanted to know the infiltration rate right at 0.1 hours. And so the infiltration rate is declining over time. So it's not a linear rate. The infiltration rate started high, then it was decreasing. So what we've just calculated isn't the infiltration rate during the 0 to 6 minute period. This is the infiltration rate right at 6 minutes. And so the infiltration rate 5 minutes into the storm was higher than this, and the infiltration rate a minute later is going to be lower. This is just the instantaneous infiltration rate right at 6 minutes. So that's why we didn't just divide this infiltration depth by the period over which it occurs. This is an instantaneous rate. So any questions so far? And as you'd maybe guess, this second part of the question is going to be pretty straightforward because we've got these anchored references. So now find the infiltration depth and rate 0.2 hours. So our first time was 0.1, now at 0.2 hours. So now we're talking 12 minutes into the storm. We can drag this, well, this first one's just a guess. And so we started off with 1 centimeter. That's a fine place to start. Drag this formula down, and that one. We're going to have to let goal-seek or solver run again. We'll use solver. So this time we want the difference in row 11 to be minimized down to 0 by changing our guess value. So same as before, solve. All right. So, of course, the infiltration depth is higher than it was before. That makes sense because think about what's happening during this storm. What we are doing is we are calculating the points that could be used to draw this curve, the capital F curve. So F is getting higher. The cumulative infiltration amount increases over time, but the rate is going to be decreasing, which is why this curve is flattening out. So now when we do this infiltration rate, you'll see that at 0.2 hours, so 12 minutes into the storm, the infiltration rate is lower than it was. So this is just a model of the declining potential infiltration rate. And it's called the potential infiltration rate because it assumes continuous ponding. And if you don't have continuous ponding, then you won't have had this much water going in. So after 0.2 hours, we're assuming, 0.2 hours, we're assuming that 0.375 centimeters of water could get down in there. Now, most storms are going to, most storms like design size storms are definitely going to satisfy that continuous ponding assumption. But that is something you need to be sensitive to is looking at what's the rainfall amount. And if the rainfall amount is less than this, then it would only infiltrate how much has rained. But if the rainfall is more than this, so let's say that the rain was 1.5 centimeters in the first 12 minutes. So if the rainfall was 1.5 centimeters, then the runoff would be 1.5 centimeters minus the infiltration amount. So you could use this to predict how much runoff there's going to be, the depth of the runoff. And of course, the volume of the runoff would be the runoff depth multiplied by the area of the watershed. Any questions? All right. I think you've got a homework problem pretty similar to that. Pretty similar. All right. So we can also use these related ideas to calculate how long it takes for ponding when the storm is low. Like in a storm where the potential rate of infiltration initially exceeds the rainfall intensity, then there's going to be a certain amount of time until the ponding occurs. And so, like, it's not at the beginning of a storm that suddenly all of the pores above the water are full. And so it may take, the storm a little bit so that it starts to fill the soils voids, and then you'll start to see ponding. And so if you have a curve of the declining potential rate of infiltration, that's lowercase f, we want to calculate the T sub p, the time to ponding. And you can calculate the depth of water that's infiltrated at that time. It's just going to be the rainfall intensity multiplied by the time to ponding. And so you can only have as much water getting into the soil as you've had rainfall intensity. And so the overall depth would be, you can see here on this figure it was inches per hour. So if you multiply that by hours, then that would give you the cumulative infiltration depth up till that time. So here's the formula that we can use to calculate the time to ponding. And if you look at the parameters in the numerator, we've got the hydraulic conductivity, the suction head, delta theta, and then down below is the rainfall characteristics. The rainfall intensity is being taken into account. So let's look at this next part of the example. We have the same 45% initial effective saturation. So that was the same as before. And let's say that we had a storm of 1.5 centimeters per hour. So how long is it going to take until the ponding occurs? Because the initial rate of infiltration may be higher than that. These are the same values as we had in the previous example. And so I think, do you have another tab that looks like this in yours? All right, but yours doesn't have the answers in it, so let me get those out of there. All right. Same soil as before, just now we actually have an idea of what the rainfall intensity is. Okay, so the effective porosity for the soil was 0.423. The suction head was 29.22 centimeters. The hydraulic conductivity, 0.05 centimeters per hour. The effective saturation, 0.45. And then the delta theta, calculate that same as before. It is 1 minus S sub E times theta sub E. Okay, so 0.232, same as it was before. Okay, so this is asking us how long is it going to take until ponding occurs? And so by definition, what that means is we're solving for some time where the rainfall curve intersects the cumulative infiltration curve. So the rainfall intensity during this early stage of the storm is constant, 1.5 centimeters per hour. So we're going to try and find out when would that rainfall depth that occurs after a certain period of time match up with the cumulative infiltration. So this is kind of like a graphical solution looking for the point of intersection between the rainfall and the infiltration depth. So we don't know the time, so we'll just say a guess time 0.05 hours as a starting point. And the 0.05 is going to have a guess for the depth. So we just have a guess depth of maybe 0.5. Now we'll do maybe 1. That was our guess in the previous examples as well. Now here on the right-hand side of the equation, we're going to be referencing this guess time. So let's now set up the formula so that it's referencing this guess time point. Okay, so equals K times T plus the suction head times delta theta times the logarithm. By the way, I'm not bothering to anchor the references because I'm not going to drag this down through any other rows. F sub t divided by psi times delta theta. Oh, I need to put another parentheses in the denominator to make sure that it's dividing by both of those. Okay. Okay, so the difference is one minus the other. All right, so what we want to do is we want to find out how long is it until the cumulative infiltration depth is the same as this 1.5 centimeters per hour. Okay, so I'm going to do solver just using up to 0.05 hours, and we'll find out what was the cumulative infiltration depth up to that point. So our difference is 0 by changing this guess value. Okay, solve, and we'll keep the solution. Okay. The storm intensity 1.5 centimeters per hour, and the time that we have 0.05 hours. Here, let's calculate the precipitation intensity times the time. So the intensity is 1.5 centimeters times this time. So right now, these two aren't equal. The infiltration amount and the precipitation amount isn't equal. So that means that the time to ponding guess that I've got in here is too low. So it's not at 0.05 hours that the precipitation depth is equal to the infiltration depth. What's that saying is that the infiltration rate is still higher than the precipitation amount. So we're to the left of this point. So we're at the point where the capacity for the soil to infiltrate water is still higher than the precipitation rate. And so if we did another time, 0.1 hours, then we would have to run the goal seek again. So same as before, we're still getting the difference to 0 by changing this guess. Oh, our objective is this by changing that. Okay, solve. Okay, we're getting closer. Now, if we're 0.1 hours into the storm, then we would have 0.15 centimeters of precipitation, but that's still less than before. So what we need to keep doing is we need to keep gradually increasing until we found the amount of time that gives this infiltration depth the same as the precipitation depth. And so it's kind of like a solver within a solver, because we have to do the solver one time to make these two equal to each other, and then we have to do the solver another time so that this is equal to is the infiltration amount is equal to the precipitation amount. Okay, so this is just asking us what rainfall intensity would cause ponding after 20 minutes. So after 20 minutes, that's a third of an hour. So if we had the precipitation, well, I'm not sure if we've addressed the first part of this question. How long until ponding occurs? So the ponding occurs when the this depth equals that. So we're still not there. 0.2 hours. Looks like we may have overshot it at 0.2 hours because now the precipitation amount is greater than. Let me just do the goal seek again. Solver. All right. So it's less than 0.2, 0.18. Getting pretty close now. Okay, we're too far. So, you know, at 0.35 hours, then that tells us that the infiltration amount is less than the rainfall amount. So we're just looking for where do those two curves intersect. So maybe 0.33. This may be as close as we're going to get. So in a third of an hour, what we see is that the precipitation amount, 0.495 centimeters, and the infiltration amount, 0.485. So that's basically just more precipitation than infiltration amount. So we're at the point now where these two curves have intersected. All right, so the initial question was asking, here in part A, how long until ponding occurs? Let's say 20 minutes. And what rainfall intensity would cause ponding after 20 minutes? It would be 1.5 centimeters per hour is the rainfall intensity that causes ponding after 20 minutes. And how much cumulative infiltration happens during that during a period of 0.156 hours? And so let's look at 0.156. And we have to do the solver again so that the left-hand side and the right-hand side are equal. So in 0.156, the infiltration amount is 0.331 centimeters. I guess maybe just to make it explicit, the units of this is centimeters. You know, as we're going back and forth and comparing this value to the infiltration, this is the precipitation